So I'll explain another problem. So this is the third problem under concrete mix proportioning. So as per 1026 to 2019. So this problem is quite different compared to the other problems that we have solved. I'll tell you where are some changes. Okay. So in the question, this is one of the question paper problem that I have taken from the question paper. So it is required to design a concrete mix for a pile foundation of the structure. So you know what do you mean by pile foundation? So there are two types of foundation. One is shallow and the deep foundation. I think you might have studied in building construction. So a pile foundation comes under the category of deep foundation, where if any multi-story building is going to construct, or if any mass construction is happening, or if the soil is not good to take up the load, then they will go for a deep foundation. So in deep foundation, one of the best uh, method of constructing the foundation is the pile foundation. So these are the datas that is required to do the mix design. Characteristic strength at 28 days, that is 45 Newton per mm square, that is M45. Directly they have not given M45. Instead of that, they have given the characteristic strength at 28 days. So the value is 45 Newton per mm square. That means it is FCK. Okay. Type of cement OPC 53. Then maximum nominal size of aggregate 10 to 20 mm. So 10 to 20 mm in the sense in that the maximum size of the aggregate is 20 mm. So it is 20 mm down size. So meaning of 10 to 20 mm means it is 20 mm down size. In that whichever is maximum, you have to take that value for the mix proportion. Next, exposure condition very severe as per the durability aspects as per IS 456 2000. Next, method of concrete placing pumpable concrete. So here method of placing the concrete is by pumping. Next, degree of supervision, it is good. That means all the quality of the aggregates and whatever the test that they have carried out, it is under good quality. Next type of aggregate, subangular aggregate. So usually it will be crushed angular aggregate or subangular aggregates. Then minimum cement content 340 kg per m cube. So as I already told in the last problem, if they give very severe, then you should be able to take the value of minimum cement content and maximum water cement ratio from the codebook of IS 456. If they don't give IS 456 codebook, then you should be able to know for what type of exposure condition, what is the minimum cement content and what is the maximum water cement ratio. Don't expect every time that they will give the value. Okay, so 80% of the time they will give. Okay, but remaining 20% I am not sure. Also, if they give exposure condition, then you should be able to know the value of minimum cement content and maximum water cement ratio. In this case they have given. Okay, so 340 kg per m cube and maximum water cement ratio 0.45. Chemical admixture type, super plasticizer. So they have used the chemical admixture because the slump required is high. So 125 mm slump, without using admixture you won't get the workability in that range. Okay, so chemical admixture they have given. Next, mineral admixtures they have used fly ash, because for mass construction or for heavy construction, most of the times they use both chemical and the mineral admixture. So mineral admixture it is given fly ash, conforming to IS standards. Next, very important thing is the data given in MNN. Okay, so standard deviation after testing 30 samples. So till now, this standard deviation we used to assume from the IS 1026 to 2019. So in this case, the standard deviation is given in the problem. It is after testing 30 samples. So they have found the standard deviation as 2 Newton per mm square. Okay, so this data is given. Next, air content entrapped. So volume of air content also we used to take the value from the codebook based on the maximum size of the aggregate. But here the air content entrapped is also given in the data. Okay, so these two you should keep in mind. Okay, next, test data for materials. Specific gravity of cement 3.15 standard, specific gravity of fly ash 2.2, then specific gravity of the materials in SSD condition, that is saturated surface dry condition, Coarse aggregate 2.70, fine 2.60, and admixture 1.145 standard. uh, Specific gravity of coarse and fine, it will vary as you all know from 2.6 to 2.8, whereas admixture and cement content, cement specific gravity, most of the time it will be same, that is 3.15 for cement and 1.145 for admixture. Next, water absorption, coarse aggregate 0.5% and fine aggregate 1%. So this data. Next, free surface moisture. So coarse aggregate they have given it as nil, and fine aggregate they have given it as 2%. So in the last problem, they gave the total moisture present in the aggregate. From the total moisture present in the aggregate, we derived the value for the fresh surface moisture. Okay, by taking a difference between total moisture content and the water absorption. Okay, that is in the last problem. But in this problem, directly they have given free surface moisture. They have told coarse aggregate nil, and fine aggregate they have told 2%. That means coarse aggregate is in dry condition, fine aggregate is in wet condition. Okay, so this is sometimes they will ask in this way also, just to uh, get the students to confuse. Okay, so coarse aggregate nil in the sense the coarse aggregate is in dry condition. Okay, fine aggregate 2% means fine aggregate is in wet condition. Okay, so sometimes this type of condition that will happen in the site where the coarse aggregate will be in dry condition when the fine aggregate is stored in a bin or in the silos. If there is any moisture present in the silos or bin, then fine aggregate will be having some moisture in it. Okay, so that's why this is the value. So coarse aggregate is in dry and fine aggregate is in wet condition, because the value of free surface moisture is given for fine aggregate. Then based on the sieve analysis test, so coarse aggregate most of the times it will be conforming to table 7 of IS 383 2016. Okay, so coarse aggregate need not worry much because it will be conformed to table 7 most of the times. Fine aggregate is the one which you have to take care, because there are 4 zones as you all know from IS 383 2016. So in this case, the fine aggregate is conforming to zone 3 of table 9 of IS 383 2016. So you should be knowing which zone they have given. Okay. So zone 4 most of the time it is not used for RCC works, because it is the sand that is obtained from zone 4 is very finer. Okay. So either you will get zone 1, zone 2 or zone 3. So these are the test data for the mixed proportion. Okay. So next, first step. So well, I think you might be knowing by this time. So what are the different steps that comes in an order? Okay. So we have done 2 problems. We have done the have explained the procedure also. So you know what are the steps that is starting from first. So first step is target strength for mixed proportioning. So you know that formula, there are 2 formulas are there. F dash ck is equal to fck plus 1.65 into s, and one more is f dash ck is equal to fck plus x. Okay, so next here the very important thing is when you take f dash ck 45 plus 1.65 into s. Okay, so s is already given in the data, so you should not take the value of s from the codebook. That's why I have removed the table also. Okay, I have not taken a screenshot of the table also. Why? Because the value of standard deviation after doing 30 samples, after doing the test for 30 samples, they have found out that the standard deviation is 2 Newton per mm square. Okay, so you know how to do the standard deviation test also have explained when I did the procedure. So based on that test, they have found the standard deviation as 2 Newton per mm square. So you should not assume you should not take the value of standard deviation from the code book. Okay, so that is one at one point you have to be very careful. So 45 plus 1.65 into 2. So 2 is based on the date of standard deviation given. So you will get 48.3 Newton per mm square. And one more formula is there, f dash ck is equal to fck plus x. So fck is 45, you have found out, and x is 6.5. I have highlighted it for M45 grade concrete. The value of x is 6.5. So the value is 51.5. So out of these two, whichever is the higher value, it should be adopted. You know that. Okay. So the higher is 51.5. So 51.5 is the target strength after doing 28 days test. Okay. So when you do the compressive strength after casting the concrete based on this proportion, as you all know, the strength, it should be obtained in between 45 to 51.5. Only 5% of the results can fail. That is, only 5% of the results can be less than 45 Newton per mm square, whereas other 95% of the results should be in between 45 to 51.5. Okay. So next, appropriate air content. So uh, this is usually I used to give the data. Okay, so with the table and with the explanation for 20 nominal size, the volume of aggregate is 1% based on the uh, data given in the code book. But in the question, the data is already specified that the volume of air entrapped is 4%. Okay, you should not take 1% here. Okay, you understood, right? If you take 1%, then the mixed proportion at the end, it will be wrong. So that's why the data, that whatever the data given in the problem, you should read very carefully, and then you have to take the value based on the steps that you have come across. So here, data given, I have already at the bottom I have given. So data given is air content entrapped is 4%. So here you should not take 1%. Okay, so I think I have cleared in this step. Next, selection of water cement ratio. It is the same thing based on the figure 1 of IS 10262 2019. So the target strength based on the two values, the highest is 51.5. So for 51.5 and curve 3. So what is curve 3? So curve 3 is for OPC 53, curve 2 is for OPC 43, and curve 1 is for OPC 33. So in our data, they have used OPC 53. So you have to take curve 3. So from the y-axis, that is the compressive strength of concrete, so the target strength is 51.5. So from 51.5 you should draw a line so that it touches the curve 3, and then you have to drop the vertical line so that it touches the x-axis, that is the water cement ratio. Okay, I have highlighted in a red color. So from 51.5 touching curve 3, and from curve 3 you have to drop vertical line so that it touches the water cement ratio. So that water cement ratio from this figure 1, so it is 0.38. Okay, have approximated to 0.38. Okay, so whereas the maximum water cement ratio given in the data is 0.45, or from the code book also you can refer. So I have put a screenshot at the bottom. For very severe condition, the maximum water cement ratio is 0.45. So out of these two values, that is one from the curve and the another from the code book, so out of these two value, whichever is lesser, you have to adopt that as the water cement ratio. Why? Because lesser the water cement ratio, greater will be the strength. So that's why out of these two, whichever is lesser, you have to adopt that as the water content. So out of 0.45 and 0.38, the lesser value is 0.38. So we are adopting 0.38 as the water cement ratio. Next, selection of water content. So this step also I think you are more familiar. So for 20 maximum size of the aggregate, the water content is 186. So I have highlighted it. Okay. So as per the code, but the slump required is 125 Okay. So the estimated, whereas this table is for 50 slump, so you require the water content for 125 slump. So as per the code, as you know, in the previous two problems we have done this. So for every 25 increase in slump, you have to increase the water content by 3% as per the code. So now I have just split up 186 for is for 50 slump, then 3% of 186 is for 75, another 3% of 186 is for 100, and another 3% of 186 is for 125. Instead of giving 9 by 100 of 186, I have just split it into three parts so that you will able to understand. So after calculating the value, then you will get 202.74 kg or liters. Okay, I think you understood the previous step. So 186.4 is for 50 slump. So as you know, as per the table, so the table is for 50 slump. Then we require the slump for 125. That means we have to increase the water content for another 75 slump. So I have split 75 into three parts. So for every 25 increase in slump, we have to increase the water content by 3%. So 3% into 186 into 3 times, it increases the water content for another 75 slump. So that gives the value of 202.74. Then since we are using chemical admixtures, so if even if you use chemical admixture and water content both at the same time, then there will be more water content in the concrete, so that leads to highly workable concrete. Okay, so if it is highly workable concrete, then there is a chances of segregation or bleeding. So that's why if you are using chemical admixture, then we have to reduce the water content by some amount. So in the code book they have told that it is in between 20 to 30% you can able to reduce the uh, water content. So here I have assumed that you can able to reduce the water content by 25% based on the codal provision. So the arrived water content is, so if you are reducing 25% means remaining is 75%. So 202.74 into 0.75, that is 75%, you will get 152.05 kg. So I have approximated to 153 kgs. So this is for water. Next, calculation of cement content. So you know water cement ratio we have calculated as 0.38, so that we have obtained in the third step. Then cement content is equal to W by C, that is in the numerator it is the water content, in the denominator it is water cement ratio. So ultimately you will get the cement content. So water is 153. After after reducing the water content by 25%, the value obtained is 153, divided by 0.38 is the adopted water cement ratio. So if you do that, you will get 402.63. So I have approximated to 403 kg per meter cube. So here you know that we are using the mineral admixture also, that is we are using fly ash also in our mix design. So if you are using fly ash, as I told in the last problem, you these 2 points you have to keep in mind. This is there in the code book also, you can refer. So decide the percentage fly ash to be used based on the project requirement and the quality of fly ash. So when we doing the mixed design, so we should decide what is the percentage of fly ash to be used for the replacement of the cement. So this proportion has to be decided prior to the mixed proportion of the concrete. So here this percentage, it depends. Okay, usually we use 10, 20 or 30 because there are so many research on this. So the ideal is you can replace the cement by 20 to 30%. Okay, so if they don't give the value, what should be the percentage of fly ash to be used in the mixed proportion, then you have a uh, then you can assume the percentage of fly ash to be used in the mixed proportion. Okay, so you have a liberty of that. But when you are selecting a suitable percentage, don't take 40, 50, 60 and all. Okay, so the ideal percentage replacement of fly ash or GGBS is in and around 20 to 30%. Okay, so 20 to 30% is ideal. So in the last problem, I guess GGBS I have taken 30% replacement. So in this problem, you can take around 20%, or even you can take 30% as the replacement. So B is very important, what I have written there in the B point. In certain situation, increase in cementitious material content may be warranted. So now 403 kg per m cube is the cement content that is obtained. Okay, now you are adding fly ash also. Fly ash also having certain cementitious property in it. Okay, you know that. So I have studied the mineral admixture chapter. So there, you know, fly ash also has certain mineral, also has certain cementitious property. So you are adding that to the cement. Now the percentage of some chemicals composition will get increased. Okay, so that's why we normally used to tend the we normally used to increase the percentage of cementitious content. Okay, not every time. Okay, last problem we didn't do that. Okay, because uh, fly ash and cement, most of the chemicals present in it are same, whereas in GGBs it is not like that, it is slightly different. So that's why there we didn't increase the percentage of cementitious material content, whereas here since we are using fly ash, so the chemicals present in it is most are same related to that of a cement. So here, so we are increasing the percentage of cementitious content by 10%. Okay, so cementitious material content we are increasing by 10%. Okay, so increasing means it is 10% extra compared to what we have. Okay, so 403 into 1.10, 1 means you are increasing by 10%, so that's why it is 1.10. If you are decreasing by 10% means then you have to multiply by zero point 0.9. So here we are increasing the cementitious content by 10%, so 403 into 1.10, we'll get 443.44 kg per m cube. I have approximated to 444. So this percentage of increase you can do only if you are using fly ash, or if you are using silica fume, then you can increase the percentage of cementitious content. If you are using GGBS, then not required. Only when fly ash or silica fume if you are using, then you can increase the percentage of cementitious content by 10% as per the codal provision. So 403 into 1.10, you will get 444 kg per meter cube. So now you have increased the percentage of cementitious content. Okay, so instead of 403, now the percentage of cementitious content is 444. Okay, but in order to maintain the water cement ratio, you have to do the water cement ratio calculation once again. So 153 was the water content that is obtained from the previous step. By 0.38 we did, okay, to get the cement content. Now to get the water cement ratio, what we have to do, 153 is the water content and 444 is the cement content. So water cement ratio means W by C. So W is 153 and C is after increasing the 10 percentage of cementitious content. So now 153 by 444, you will get 0.34. Earlier the water cement ratio was 0.38. Okay, so after increasing the cement content by 10%, now the water cement ratio is still reduced, and also it is still within the limit. So it is also still within the maximum water cement ratio, so then no problem. Okay, so only when if it exceeds the maximum water cement ratio, then it is a problem, otherwise it is not at all a problem. Okay, so now here the fly ash percentage that we use is 20%. So as I told, the ideal is in between 20 to 30, or if they give the data in the question, you can use that data only, or else you can take the percentage replacement of fly ash in between 20 to 30. So in this problem I have taken 20. So fly ash at 20 percentage of total cementitious content, so 444 into uh, 0.20, so that is 89 kg per m cube. Okay, so percentage of fly ash at 20% means out of total cementitious content of 444, so we are using only 20% of the fly ash. Okay, so 444 into 0.20, you will get 89 kg per m cube. Now what is the cement content, what is the OPC content that we are using in the concrete mix proportion? So 444 is the total cementitious content after increasing it by 10%, minus 89 is the fly ash content, so remaining is 355 kg per m cube. Okay, so you can see the value 444 and 355. If you take the difference, you'll get 90 kg. So approximately you can able to save 2 bags cost of cement for 1 meter cube. So if you take for whole construction, then you can save a lot of money. So that will be the economical structure. So if you use fly ash or GGBS, then you can able to reduce the cost, as well as there are certain cementitious properties that will enhance if you use mineral admixtures also. Okay, so now 355 of cement content, whether it is within the limit or not. So for very severe exposure condition for durability aspects, so the minimum cement content is 340. So whatever the cement that we have got is 355. So as I already told in the previous two problem, so whatever the value of cement content that you get, it should be in between the maximum minimum cement content and maximum cement content. So minimum cement content is 340, and whatever the cement you obtained is 355, and maximum is 450. So whatever the value that we got, it is within the limit. Okay, as per the IS standards. Okay, so I hope you understood this step. If you have any doubt, you can ask me at the end. Okay, if you have any doubt in this step, you can ask me at the end. Next is proportion of coarse aggregate and fine aggregate. So here also I have already told in this table. So this table is given for the water cement ratio of zero point 0.5. Okay, so for 0.5 water cement ratio, based on the maximum size of the aggregate and based on the zone of the fine aggregate. So maximum size of aggregate is 20 and the zone given in the problem is zone 3. So for 20 maximum size and based on zone 3, the value is 0.64. So that value of 0.64 is for the water cement ratio of 0.5. Okay, so for 0.5 the water cement ratio is 0.64. Now in our case the water cement ratio is 0.34. So whatever we found it in the third step as 0.38, so that we have to neglect it because we have increased the percentages of cementitious content. So when you increase that, then we have a new water cement ratio of 0.34. Okay, so in our present case the water cement ratio is 0.34. So compared to the benchmark of zero point 0.5, our water cement ratio is decreased by 0.16. Okay, so as per the code, you know that for every 0.05 you have to for every 0.05 decrease in the water cement ratio, you have to increase the volume content by 0.01. So it is in the code book. Okay, so here also 0.16 I have split into four parts. So 0.05 plus 0.05 plus 0.05 plus zero point zero 0.01, I have splitted 0.16 into four parts. So for every 0.05 increase, for every 0.05 decrease in water cement ratio, you have to increase the volume on the right hand side by 0.01. So for 0.05 decrease, I have increased by 0.05, zero point zero 0.01. For another 0.05 decrease, I have increased by 0.01. For another 0.05 decrease, I have increased by 0.01. For another 0.01 decrease, I have increased the coarse aggregate volume of coarse aggregate by 0.002. If you add all this, you will get 0.032. Okay, so now the corrected proportion of volume of coarse aggregate for the water cement ratio of 0.34 is equal to 0.64 plus whatever the proportion of volume aggregate that we have increased on the right hand side, you have to take. Okay, 0.64 plus 0.032, you will get 0.672 cubic meter. Okay, I hope you understood this step. Okay, this is very important step also. So zero point 0.5 for in the table it is given for zero point 0.5 water cement ratio. Based on whatever we got the water cement ratio, we have to make some adjustment on the right hand side. That is, right hand side is volume of coarse aggregate. Okay, so in this case our water cement ratio is decreased by 0.16. So that's why on the right hand side you have to increase it by 0.032. How you got 0.032 I have explained already. So for 0.34 water cement ratio, the volume of coarse aggregate is 0.672 cubic meter. Now, in the method of placing in the data, you know that we have done, means they have given in the data that the method of placing is done by pumping. So for if you do the method of placing by pumping, then you have to decrease the you have to reduce the volume of coarse aggregate by 10%. So I have highlighted in the pic. Okay, you can see there. If you are doing method of placing by pump, then you have to decrease the water content, then you have to decrease the coarse aggregate content by 10%. Okay, so now therefore if the method of placing is not by pumping, then no need of doing this step. Only if it is done by pumping, you have to do this step. Okay, so now the volume of coarse aggregate is 0.672, that is obtained from the previous data. 0.672 into 10% reduction. 10% reduction means another 90% is remaining. So 0.672 into zero point 0.9, so you will get 0.604 cubic meter. And volume of fine aggregate is 1 minus of coarse aggregate, that is 1 minus of 0.604, you will get 0.396 cubic meter. Okay, I hope you understood this step. So next is mix calculation. So as you all know, we are doing mix calculation for 1 cubic meter of concrete. So volume of entrapped air is 4% given in the data, so it is 0.04. Then volume of cement is equal to formula, it is given in the code book also, or you can refer in the slide. So mass of cement divided by specific gravity of cement into 1 by 1000. Mass of cement is 355 after deducting the mass of the fly ash, okay, from the total cementitious content. So 355 divided by 3.15 into 1 by 1000, you will get 0.112 cubic meter. Then volume of fly ash, then is equal to mass of fly ash, that is 20% of the total cementitious content, you will get 89. So 89 divided by 2.2, 89, you know how you got. So 444 into 2.20, you got 89. So 89 divided by specific gravity of fly ash is 2.2. 89 by 2.2 into 1 by 1000, you will get 0.040 cubic meter. Volume of water, so mass of water, so you should take mass of water after reducing 25% of the water content by admixture. So 153 was the water content, 153 by 1 is the specific gravity of the water, into 1 by 1000 you will get 0.153 cubic meter. Then volume of chemical admixture also we are using. So volume of chemical admixture, so in the previous problem dosage was given in the data, So if they given in the data, you have to take that percentage of dosage only. Otherwise, you can start with 1% of the total cementitious content. So formula is mass of chemical admixture divided by specific gravity of admixture into 1/1000. So mass of chemical admixture means it is 1% of the total cementitious content. So total cementitious content is 444. That is after increasing it by 10%. So 444 into 1% of the dosage of chemical admixture. 1% means 1 by 100, you will get 0.01. So 444 into 0.01 divided by 1.145 is the specific gravity of admixture into 1 by 1000, you will get 0.0038 cubic meter. So now all the materials we have taken, the another material that is left is volume of aggregates. So to find the volume of aggregates, we have to deduct all these values from the total volume of concrete. So total, that is the volume of aggregate, is equal to 1 minus of 0.04 minus 0.112 minus 0.040 minus 0.153 minus 0.0038. So if you deduct all these values from the total volume of concrete, the remaining is the volume of aggregate. The value that you will get is 0.651 cubic meter. Okay. So now mass of coarse aggregate and fine aggregate we have not found. So to find the mass of coarse aggregate, we have a formula: G into volume of coarse aggregate into specific gravity of coarse aggregate into 1000. So G means whatever the notation, that is volume of all the aggregates 0.651, and volume of coarse aggregate we have found here, that is 0.604, into specific gravity of coarse aggregate. I have taken a data screenshot of the data, 2.7 into 1000, you will get 1061.65 kg, approximated to 1062. Then mass of fine aggregate, same formula: G into volume of fine aggregate into specific gravity of fine aggregate into 1000. So G is total volume of all the aggregate 0.651, and volume of fine aggregate is 1 minus of 0.604, you will get 0.396, you obtained from the previous step, into 2.60 is the specific gravity of fine aggregate into 1000, you will get 670.26 kgs. So I have approximated to 671 kg. So list out all the masses, that is in the mixed proportion for trial number 1. So cement is 355, fly ash is 89, water is 153, fine aggregate in SSD condition is 671, coarse aggregate in SSD condition is 1062, chemical admixture 1% of the total cementitious content 444 into 0.01, you will get 4.44 kg per m3, and free water cement ratio is 0.34, it is not 0.38. Okay, it is 0.34. So after increasing the total cementitious content, the water cement ratio has changed from 38 to 34. So this is the mixed proportion for trial number 1, but you know it is for SST condition. So fine and coarse aggregate is for SST condition. Now as per the data, coarse aggregate is in dry condition, whereas fine aggregate in wet condition. So we have to do some adjustment for coarse aggregate as well as for the fine aggregate. So adjustment on water, fine aggregate and coarse aggregate. So if the coarse and fine aggregate is in dry or wet condition, you have to do some adjustments. So now I have taken a screenshot there. You can see in the picture, for free surface moisture, coarse aggregate nil, fine aggregate is 2%. That means coarse aggregate nil means it is in dry condition, fine aggregate 2% means it is in wet condition. So the formula slightly changes for both. Okay, now fine aggregate is in wet condition. So the formula is mass of fine aggregate in SSD condition into 1 plus of free surface moisture by 100. Okay, free surface moisture by 100. This formula is for the wet condition. Okay, the mass of fine aggregate in SSD condition is 671 into 1 plus of free surface moisture for fine aggregate is 2%. So 2 by 100, you will get 684.42, have approximated to 685 kg. Okay, next coarse aggregate, in the bracket it is given as wet, sorry, it is in the dry condition. Okay, please make a note there. For coarse aggregate, it is not wet condition, it is a dry condition because it is nil. So mass of coarse aggregate in SSD condition, the formula there you can see between wet and dry. So slightly there is a change. Okay, for wet aggregate it is into, whereas for coarse aggregate in dry condition it is divided by. So mass of coarse aggregate in SSD condition divided by 1 plus of not free surface moisture, because free surface moisture it is given as nil, so it will be 0. So now here you have to take water absorption for the dry condition. So water absorption for dry condition is 0.5%. If you see in the data, you will get to know. So mass of coarse aggregate in SSD condition is 1062 divided by 1 plus of water absorption for coarse aggregate is 0.5 divided by 100, you will get 1056.71 approximated to 1057 kg. You can see the difference there. For fine aggregate compared to SSD condition, in a wet condition it has been added, means it has increased from 671 to 685 kg, because the fine aggregate is in the wet condition, whereas coarse aggregate is in dry condition. So that's why from SSD condition to dry, from 1062 it has been got reduced to 1057 kg, because it is in the dry condition. Okay, now uh, there is some amount of water has to be increased and some amount of water has to be decreased for the total water content. So that will do in the, that will see in this step. So extra water to be added for the coarse aggregate. So mass of coarse aggregate in SSD condition is 1062 and in the dry condition that we obtained is 1057. Okay, so to make the aggregate wet, you have to increase the water content by 5 kg, whereas for fine aggregate it is already in the wet condition. So for mass of fine aggregate in wet condition is 685 and mass of fine aggregate in SSD condition is 671. If you take a difference, you will get 14 kg. That means there is 14 kg of extra water present in the fine aggregate. So now the total required water is 153 is the water content that we arrived. Then plus 5, plus 5 is to make the coarse aggregate into moist content, because it is in the dry content, it is already dry. So you are adding extra water for coarse aggregate, that is 5 kg, whereas for fine aggregate it has already more water present in the material, that is the fine aggregate, so you are reducing it by 14 kg. So this is a tricky part in this problem. Okay, so in the first two problems that we solved, both the problems, in the first problem it was both the material it was in dry condition. In the second problem both the material was in wet condition. So in this problem coarse aggregate is in dry whereas fine aggregate is in wet. Okay, so for the total water content, we have to add the water content for coarse aggregate which is in dry condition. Similarly, we have to deduct the water content because the fine aggregate is in wet condition. Okay, so 153 plus 5 minus 14, you will get 144 kg per meter cube. Okay, so this is the required amount of water to be added by doing some adjustment for fine and coarse aggregate. Next, mix proportion after adjustment for wet and dry aggregates. So cement is same 355, fly ash is same 89, water compared to 153. After doing adjustment, it has become 144. Now fine aggregate is in wet condition because free surface moisture is given. So 671 was the fine aggregate uh, value. So now it has been increased to 685 kg because it is in wet condition. Whereas coarse aggregate in the SSD condition it was 1062. Since there is no free surface moisture, it has become dry. So now the value has become 1057 kg per cubic meter. Next, chemical admixture remains the same 4.44. That is 1 percentage of the total cementitious content. 444 into 0.01, you will get 4.44, and free water cement ratio it is same 0.34. Now the total mix proportion is uh, total cementitious content was 444. If you add cement and uh, it is there as GGBS. Sorry, I didn't edit it at fly ash. So fly ash is 89. Sorry, it was GGBS. Sorry, it is there as GGBS, so change it to fly ash. So cement is 355, fly ash is 89. If you add these two, you will get 444. So one proportion of 444. Next, fine aggregate is 685. So 685 divided by 444, you will get 1.14. 1057 divided by 444, you will get 2.38. So this is the final mix proportion after adjusting for wet and dry conditions. Okay, so did you understood? So this is the final step. Okay, so I hope you understood the mixed proportion for this kind of problem also.